In Unit 4, we will discuss the principles of serological testing in immunohematology. Let's briefly discuss blood group antigens and antibodies. Blood group antigens are embedded structures that are in or protruding from the red cells, white cells, or platelets. Exposure to blood group antigens that we do not possess through transfusion or pregnancy may initiate an immune response. Individuals may form antibodies to the antigens they're exposed to that they lack. We are most concerned with IgG and IgM class antibodies. IgM are also called naturally occurring antibodies because they occur without exposure through transfusion or pregnancy. There are things in nature very similar to some blood group antigens that cause them to be produced naturally. They react at room temperature and they're very easily detectable. IgG are known as immune antibodies, and they require actual exposure to the antigen, and they require special serological tests, the Coombs test, to detect. We're always testing for antibodies in serum or plasma and antigens on cells. In the transfusion service, that is what we're doing 7 days a week, 24 hours a day, testing for antigens on cells and antibodies in the plasma. So as I said before, we're always detecting antigens on cells and antibodies in serum. So detection of antigens is routinely done to determine an individual's ABO and D type. We take known typing sera and test it against unknown cells. So we have anti-A, which will detect the A antigen, anti-B, which will detect the B antigen, and anti-D, which will detect the D antigen. So these are very easy to perform and very sensitive and specific. Antibody detection tests are used to confirm ABO antigen typing, because if you are a group A individual, you will have anti-B in your plasma. If you don't, then that's an ABO discrepancy, and we need to figure out what is wrong. Detect unexpected antibodies, and these are antibodies other than ABO in the serum or plasma, which may cause destruction of transfused cells containing the antigen. So again, if you've been transfused or pregnant, you may develop an immune antibody, and these immune antibodies will react with antigen on donor cells if they are present. It's very important for you to understand the dynamics of antigen-antibody reactions. The union of antigen with antibody depends on the structure and the charge of the molecule. Again, it's like a lock and key fit. The antibody fits specifically into or onto the antigen. Opposite charges on antigen and antibody create attraction forces, and these reactions are reversible. It's very important that you understand this because this is a cause of false negative reactions. If it says read the reaction within a certain period of time and you wait too long, the antibody may dissociate from the antigens and you could end up with a false negative. It is very important that you're aware of the physical forces which hold antigens and antibodies together and how we can enhance them sticking together rather than coming apart. The physical forces are very weak. So what that means is, again, we're having antigen and antibody combining, and then it's reversible and it'll come off. The attractive forces vary in strength with changes in pH, ionic strength, temperature, and the nature of the solvent. So these are all things that we can control and change in vitro testing. Blood group antigens and antibodies bind until dynamic equilibrium is reached. So you get to that point where no more antigen and antibody will stay bound together, and then they start dissociating. This type of dynamics is represented by a bell-shaped curve based on concentration. And again, we're bringing serology, immunology back to the front of your brain. Prozone is caused by excess antibody, and it results in a false negative. And pro is good, antibodies are good, so think of prozone antibody excess. Post-zone is antigen excess, and it will also result in a false negative reaction. What we're shooting for every day in the transfusion service is that we reach a zone of equivalence where there's just enough antibody, just enough antigen to combine together to give us a visible reaction. This picture nicely illustrates that curve we were talking about. On the left-hand side, we have the zone of antibody excess, which is prozone. There is so much antibody that it will bind to an antigen over here, it will bind to an antigen over there, but they're not in close enough proximity that we get the lattice formation. On the very right-hand side, we have postzone, which is antigen excess. There is so much antigen present that every fragment antigen binding site on the antibody molecule is coated with a different antigen. We're not getting the side-by-side connectivity of a single antibody molecule to an antigen over here and an antigen over there. It's not possible. So again, we don't get lattice formation. Zone of equivalence is what we're looking for. As you can see in this picture, there are two antibodies bound to an antigen, and then the same thing happens over and over to where we have lattice formation occurring. Detection of antigen-antibody reactions is done in a variety of methods. Agglutination is our primary way of detecting or seeing these reactions occur. Red cells have antigens which combine with antibodies that are present. The antibody bridges form with antigens on adjacent cells, and this results in agglutination. You cannot see these little bitty antibodies going on to their little itty bitty antigens. You cannot see sensitization. What you can see when enough of these form a complex, then agglutination will occur, which is a visible reaction, which is a positive reaction, indicating the presence of antibody to specific antigens. Hemolysis is caused by antibody binding, sensitization, followed by activation of complement, which results in the destruction of the red cell membrane. And the only time I've seen this occur is when a mom is a group O and she gives birth to a group A baby. If you incubate her serum long enough with the group A cells, hemolysis will occur. And that usually indicates that a baby's probably going to be affected, that the cells will be destroyed at a higher level. There are solid phase methods used to detect antigens or antibodies, but they're still based on agglutination. It's primarily done in donor centers, although they are coming into the transfusion service. Microplates are coated with antigen or antibody. If it's positive, the cells will adhere to the sides of the well because they fall out. The agglutination occurs and they fall out. If the antibody is not present, then there's nothing to combine. There's no lattice formation, so the single cells just slide to the bottom to form a button. And this is completely opposite of the tube testing that we will do, where a button is a positive. So it's kind of backwards thinking. This is why it is so important for you to know the principle of every test you perform. What is reacting with what to give what type of reaction that is positive or negative. It is crucial that you memorize the principle and the variables involved in agglutination. Agglutination involves two stages. The first is sensitization, and the second is lattice formation, and each has limitations. The first stage, sensitization, is simply the attachment of a single antibody to a corresponding antigen on the red cell membrane. The second stage is lattice formation, where bridges form between sensitized cells. IgG antibodies have one basic structural unit with two antigen binding sites. One binds to the antigen on one cell, and the other binds to an antigen on adjacent cells. IgM is a pentamer with 5 basic structural units with 10 antigen binding sites, and they can bind to several antigen sites on different cells. Lattice formation will result in hemagglutination. Hemagglutination is the agglutination of red cells. So on the left, we have IgG antibodies with lattice formation, and on the right, we have IgM antibodies. So we're going to discuss the variables affecting the first stage of agglutination, and you must know forever and ever that in the first stage of agglutination, there is sensitization. So the antigen-antibody ratio is critical. You need to determine the optimal amount of serum or plasma to be used in the test system so that we avoid prozone and postzone. If you increase the serum plasma, you will increase the amount of antibody present, so it's more sensitive. So again, many tests have been done to determine the optimal quantity of serum or plasma to use in a blood bank test. pH of 6.5 to 7.5 is what we're looking for. For routine procedures, 7.0 is used. You don't have to think about this. This has been predetermined, and all the tests performed are at the 7.0 pH. The ionic strength of the suspending medium is very important. Saline partially neutralizes oppositely charged sites on antigen-antibody molecules, which hinders association. Low ionic strength saline with lower salt concentration enhances uptake of antibody onto the cells. Albumin is a reagent that used to be routinely used, not so much anymore. Does little to affect antibody uptake onto the cell. It usually affects the second stage. It reduces the electrical charges so the antigens and antibodies can come in closer proximity. To enhance first stage reactions, the correct temperature must be used, and you must memorize this. The temperature requirements depend upon the antibody class being detected. IgG reacts optimally with the antigens at 37 degrees. Optimally means that by increasing the temperature to body temperature, it will enhance uptake of the antibody onto the antigens if the appropriate antigens are present. IgM reacts optimally at room temperature, which is 20 to 24 degrees, or very rarely we may perform some tests at 4 degrees centigrade, which is the refrigerator. So if I tell you we're testing this serum cell mixture at 37, you will know I'm looking for an IgG class antibody. If I tell you to perform the testing at room temperature, then you know I'm looking for an IgM class antibody. The incubation time, you want to choose an incubation time which favors maximal binding of antibody to the antigen. Enhancement agents will increase antibody uptake onto the cells, thereby decreasing the incubation time. So again, just remember, once we get to the optimal, there's more antibody binding to more antigen, but there's always dissociation. If you wait too long, if you incubate too long, it may result in the dynamics changing where more antibodies coming off the cells than going on, and then we may end up with a false negative. Now let's talk about variables that affect the second stage of agglutination. So the immunoglobulin class is very, very important. IgG is a small monomer, as we've talked about, with the ability to sensitize or coat red cell antigens, but not agglutinate. IgM is a huge pentamer that very easily agglutinates RBCs. Antigen sites may be present in low numbers on the surface, resulting in no agglutination. The electrostatic repulsion forces, lattice formation depends on overcoming the electrical charges that repulse or keep the red cells apart. Zeta potential is the term used to describe the electrical forces which keep them separated, and we need to use methods to decrease the zeta potential so the cells can come in close proximity, especially for IgG antibodies, to where perhaps lattice formation will occur. Additional variables affecting the second stage: you need to have an optimal concentration of antigen antibody. As we talked about before, postzone and prozone may result in false negative reactions. The effects of centrifugation. You've done ABO typing and you know there's a gentle method. You want to be gentle enough that you're not causing a false negative by shaking too hard. At the same time, we need to gently dislodge that button off the bottom of the tube. So in order to do this, the researchers, the scientists, have to determine the optimal RPMs and the optimal amount of time to spin the reactants. And you always follow the manufacturer's instructions because they may differ from reagent to reagent. Grading agglutination reactions. If you shake too hard, you will end up with either a decreased amount of agglutination or potentially a false negative. And why this is important, in ABO, if you get less than a 4+ in the forward type, then something's wrong. And especially in the reverse type, 3 to 4+ is expected. But in the forward type, it must be 4+. If you're getting less than 4+, you're shaking your tube too hard. Recognizing hemolysis as an indicator of antigen-antibody reactions. This requires the presence of active complement. So I'd like to discuss the zeta potential a little bit more because this is one of the primary factors which may cause false negatives in your reactions, especially with IgG class antibodies. This is caused by a difference in the charge density of the inner and outer layers of the ionic cloud around the red cells when they are suspended in saline. The surface of the red cells have a negative charge, and then we have all these little positive ions that will result in keeping the cells apart. It creates a repulsive electrical charge. The force keeps red cells about 25 nanometers apart in solution. So if you look at the picture, these little bitty IgG molecules have a really difficult time binding to two different antigen sites on adjacent red cells. They just can't. IgM antibodies, due to their large size, can easily cross the zeta potential and bind to antigens on adjacent red cells. I like this picture because it illustrates the charge. The surface of the red cell membrane has a negative charge, and then there's a cloud of positively charged ions. So this, in effect, allows the red cells to maintain a distance. And this is really important because if they didn't maintain distance, then they would get all clogged up in your blood vessels. We're now going to discuss the principle of the antiglobulin test. This is the most important test in the blood bank after ABOD typing. Small IgG antibodies can sensitize but rarely cause direct agglutination. They cannot overcome the zeta potential. If these go undetected, a false negative will occur, which, if transfused with antigen-positive cells, will cause destruction of those transfused red cells. In 1945, Coombs, Morant, and Race described tests for non-agglutinating coating antibodies, now called the anti-human globulin, or AHG or Coombs test. These are used interchangeably. You'll hear it all the time. AHG, anti-human globulin, or Coombs test. They all mean the same thing. You must know the principle of this test backwards, forwards, and sideways. It is the foundation of testing in the blood bank that will identify clinically significant antibodies and prevent potentially fatal transfusion reactions. A reagent antibody to IgG, which is called anti-IgG, is produced and is added to wash cells after incubation with serum, plasma, or antisera, which uses the AHG test. If the cells are sensitized or coated with IgG during incubation, the reagent anti-IgG will attach to the Fc portion of the IgG, coating the cell, causing agglutination. In this procedure, the antibody coating the cell is the antigen, which will bind the reagent antibody, anti-human globulin. So this concept is initially so very confusing to students. The fact that antibodies are antigens. And I want to say that one more time. This is anti-human globulin. It's anti-IgG. IgG is the antigen which this antibody will attach to. So after incubation, washing, if IgG antibodies have sensitized the cells, anti-IgG, when added, will then bind and cause lattice formation. You must memorize the principle of this test and be able to draw a diagram for future exams. And I'll show you several pictures, and there's also good pictures in your textbook. The importance of the Coombs test cannot be understated. Prior to 1945, they could only detect IgM class antibodies, and only a few blood groups had been identified in that time. I wish I could be a scientist back then with all these unknowns and discoveries being done. ABO antibodies and antigens were detected, but hemolysis of ABO-compatible transfused cells continued to occur. So identification of ABO was a tremendous step in the right direction in transfusion medicine. Now we knew why people were dying when we just transfused blood from one to blood from another, because if they're ABO incompatible, then the patient will most likely die. So discovery of ABO was huge. This test provided the explanation that IgG class antibodies were responsible. They could sensitize antigens but not be detected in direct agglutination tests. We just didn't have the correct methodology. It was determined that IgG was capable of destroying antigen-positive transfused red cells and also crossed the placenta, destroy fetal red cells. This test is now required. So let's look at and talk about the anti-human globulin test. So we have patient serums which have IgG antibodies. We incubate that patient's serum with reagent cells. If the antigen to which the antibody is directed is present, then we get binding of the IgG. This is called sensitization. Can't see it. After this phase, we thoroughly wash the cells to remove all of the proteins that are free, because in addition to this IgG antibody, you have IgG antibodies against measles and mumps and rubella and all other kinds of things. It's IgG. And anti-human globulin will not distinguish between bound and unbound IgG antibodies. So we thoroughly wash, and then we add the anti-IgG, the anti-human globulin. This will then cause binding of the different antigens on different cells and result in agglutination. It is important that you know the source of your anti-human globulin serum and how it was prepared. There's two methods, animal inoculation and monoclonal antibody production. In animal inoculation, purified human IgG is injected into a suitable animal, usually rabbits. And the rabbit would make anti-IgG, also known as IgG anti-human globulin. The animal is bled, the unwanted antibodies are removed, and these are then diluted and put in a bottle. Now, the animals are not sacrificed, and Gamma was one of the first companies to produce AHG serum, and they had a whole building full of bunnies, and they were the most well cared for bunnies in the world. Unfortunately, Gamma went out of business, or they got merged with another company, and the bunnies were adopted out, which I think was real cool. The IgG-AHG will react with IgG bound to cells or free in serum or plasma. I want to say that again, because again, if you have a serum sample and you've incubated the cells with this and you're looking for IgG antibodies, you have to thoroughly wash, because otherwise any IgG free floating antibodies present will neutralize the anti-human globulin serum, causing a false negative. The second method is the monoclonal reagent preparation. An animal, the mouse is most popular, is injected with the appropriate antigen, IgG, and they produce anti-IgG. They then make a hybridoma, and I want you to bring this back to the front of your brain. How they make the hybridoma is they fuse the antibody-secreting cells, which is the mouse spleen cell, with a myeloma cell, which produces massive quantities of antibodies. The myeloma cell produces antibodies without specificity. By fusing the mouse spleen cell to the myeloma cell, we are then programming the cell to produce an antibody with one specificity. And the cell is immortal. They keep culturing, and they freeze part of the culture just in case something happens and the culture dies. These cells are grown in culture, and they coat a tube which is bathed. It's a mesh, and the tissue grows, and I've seen hybridomas, and they're really gross looking, this glistening pink tissue. And they constantly bathe it with nutrients, and they harvest the fluid, and the fluid is full of massive amounts of an antibody with one specificity. I believe this picture was used in your serology course as well. So it just gives you a visual of, we immunize the mouse, we have the tumor cells, which are the myeloma cells. So we take the spleen cell from the mouse, the tumor cell, fuse them together, which then this becomes a hybridoma that's programmed to produce an antibody of one specificity. Then we harvest the secretions from those cells in order to make our reagent. Here is another picture that gives a little bit more detail of how to produce a monoclonal antibody. This is the end of part 1.